So we already have seen in previous sessions how to extract power from water. And in general, in dams, we use turbines to extract energy from water. That's why we'll talk about several types of turbines. We have impulse and reaction turbines mainly. So there are two basic types of hydraulic turbines, the impulse turbines and reaction turbines. In an impulse turbine, all pressure energy is converted to kinetic energy before hitting the wheel. So we know that in hydropower, the idea is to convert energy from one form to the other. So first you have your dam. Energy is stored in form of potential energy. So higher the height of water that you have, larger will be the potential energy that you store. Now, when you need the energy of this water, you can have an opening here, and then whenever you open the gate, this potential energy will be transformed into other forms of energy, which will be pressure and kinetic. Okay. Now, we have turbines in which case, when the water will hit the turbine, we have systems in a way that at the inlet, all pressure energy is converted to kinetic energy before hitting the wheel. So in this case, you just have conversion of kinetic energy in order to rotate, to produce mechanical energy of rotation. While in a reaction turbine, you have at this level, at the inlet of the turbine, you have both pressure and kinetic energy that will be needed to drive the blades. So we will discuss the difference between the two and how we can make calculation to know the powers that will be extracted from water turbines. So impulse turbines in general are usually useful for high head application. So as we mentioned, the head is a characteristic of the dam. So we talk about energy head in the Bernoulli equations that we developed together. You know that Bernoulli equation can be written as P over rho G plus V square over 2G plus Z equal to constant. So if we do the analysis between the free surface of the dam and just before entering the turbine, so we have this Bernoulli equation. And all terms are in meters. So this is called the pressure head. This is the velocity kinetic head. This is the hydrostatic head. And then the total head is big H. Okay. So here we can say that the purpose of the turbine is to use the water head to produce mechanical energy of rotation. And in general, if we have a very large head, we use impulse turbine. And in this case, we have low flow rates. While whenever you have lower heads and high flow rates, then you deal with reaction turbines. Okay. So now we'll see together how to make calculations in these two types of turbines. Impulse turbines are called also Pelton turbines. In this case, water is delivered at a high velocity to the wheel through a penstock. Theoretical maximum efficiency is obtained when the jet is completely reversed by the bucket. Now we'll understand what do we mean by this when we study the equation of the turbine. However, this is not always possible, and in general, the bucket exit angle is usually alpha 2 equals to 165 degrees to prevent interference with the following bucket. So now we'll try to see equations of the turbine in order to understand how we can optimize the extraction of energy from a turbine. So we just need to know a basic equation from fluid mechanics, which is the following. So whenever you have a fluid hitting a turbine, you can define velocity at inlet, and you can define velocity at outlet. And we will see together that in general, when we talk about a total velocity, the total velocity of water, V, can be decomposed into, so big V if you want, can be decomposed into two parts, which is the first one is the relative velocity of water with respect to the turbine. So you can say I should consider V relative, because if you sit on the turbine, so if you sit on the turbine, you will just see the relative velocity of water. So you can see that water is entering your turbine at a certain relative velocity. Here they called it omega. Okay. While because you do here v relative, you should add the velocity of the blade. You know, imagine yourself, take to understand this. If you have, let's say, a person in a car, okay? So let us call the person A and the car B. If you stand from outside on the fixed frame and you want to measure the velocity of the person is moving inside the car, okay? So I can say that the absolute velocity of the person, which I measure from a fixed frame, is equal to the velocity of the car, because the car will give a velocity for the person. Plus, I should add to this the velocity of the person relative to the car, which is VA relative to B. So this is why we say whenever we are finding the total velocity, we can decompose it into the relative velocity plus the velocity of given by the frame that we are standing on. So here you are inside the turbine. The turbine is rotating, so it will give you its velocity, which is r omega, because the velocity of rotation is r omega. And you should add to it the relative velocity of water with respect to the turbine. So here, the total velocity is equal to V relative plus V turbine at the point of interest. Okay? So for example, if we look at the following figure again, if we zoom it a little bit, so we have an inlet, and we have an outlet. This is the inlet. And at the inlet, this is the velocity of water relative to the blade. So this is V water relative to blade. Okay. And this is the velocity of this point on the blade. The blade is rotating. It's a blade of a turbine. So the radius is equal to R1. So we can say that this blade will give water an additional velocity component of rotation, which is the radius of this point times the angular velocity of the blade. And then the total velocity of water will be just the summation of both. So it's equal to vector u1 plus vector omega 1. Okay. Now, we do the same at the exit. So at the exit, we have the total velocity that is decomposed also into the velocity of water relative to the blade plus the velocity of the blade at this point. And as we said, the blade is rotating. So for radius R1, you have U1 equal R1 omega. And for radius R2, you have that U2 is equal to R2 omega. Now, from fluid analysis, we know that the force developed by water on the turbine can be calculated by F, force of water on turbine, will be equal to m dot of water times the velocity vector at the inlet minus the velocity vector at the outlet. So in this way, we can determine the force applied by water on the turbine. And this will help us to know how water will lead to a rotation of the turbine. So we'll not only apply this relation, we'll apply also the relation of rotation, which includes the angular momentum. So now, Until now, we defined velocities at inlet and exit, and we can write the expression of these velocities in order to be able to find what is the total torque that can be developed by this water. So as we said, we will name U1 and U2 the velocity of the wheel on the inner and outer radius. And we'll consider that big V1 and big V2 represent the absolute velocity of water. So from here, we divide big V1 into small u1 plus small v1, and big V2 into small u2 plus small v2. Now, as we know, as we said, okay, the force developed by water on the blade can be written as follow. So we said that the total, when you write the momentum equation, you can end up with the action that you can do from water on your turbine. So as we mentioned now, what is the force? It's mass flow rate m dot. And you know that the mass flow rate of water is simply the density times the volumetric flow rate of water. So m dot is in kilogram per second. So for example, if you open the gate of a dam, okay, you can know what is the flow rate that is getting out. You can express it in kilogram per second. This is equivalent to multiply the density of water, which is in kilogram per meter cube, by the flow rate of water, which is in meter cube per second. So then in total, you will get m dot equal rho times q. So this term is m dot. And as we said, the force developed on by water on the turbine is m dot times the variation of velocity, the absolute velocity, okay? And we should know that the force that is important for us is the tangential one, okay? Because you know that, let's say, if you have an axis and you have a blade, okay? And you are exerting a force on this blade. This force is decomposed into two components, one that is tangential, one that is perpendicular to the blade, and one that is normal to the blade. If you take the component that is normal to the blade, it will not produce any rotational effect because it's passing by the center. So the useful component for you will be the tangential force, okay? That's why here, when we compute the force, we'll find V tangential because this is the one that will produce rotational effect. And if we look at our figure, the total velocity is not in the, it's not tangent to the wheel. This is the total velocity. It has a certain inclination with the tangent. That's why the tangential component, we should get the tangential component of this velocity because this is the useful component for us. So as you know here, as you can see in the figures, this angle is given. So beta 1, let's say, is defined as the angle between the absolute velocity and the tangent line. Okay, so now we have to project this velocity. So we do the absolute velocity magnitude times cosine beta 1 to get the component along the tangential direction, and minus V out tangential. So also at your outlet, you have, this is the component V2, okay, the absolute velocity V2. It's doing with the tangent line an angle of beta 2. So to project it on the tangent line, we should do minus V2 cosine beta 2. And as you can see, if we just look at the expression, okay, we can try to optimize the force, to increase this force as much as possible, okay? Now, for our impulse turbine, the impulse turbine has certain characteristics. In an impulse turbine, you have that the inlet and outlet are at nearly equal radius. So R1 is equal to R2. For this reason, U1 will be equal to U2. And this will lead to a certain simplification, as we'll see now. Because if you look at your figure, you have that the total velocity is decomposed into two components, the velocity of the blade and the relative velocity. So when you do projection of Q1, it's equivalent to the projection of the relative velocity plus the projection of the velocity of water relative to the blade. So as you can see in the figure, already U is tangent to your blade, to your system. It's because you have the velocity of rotation. So let's say you have the center of rotation here. The velocity of rotation is always perpendicular to the radius. Okay, so already you have U along the tangent line. So when you project, it's equal to U1. But for the relative velocity of water, it's doing a certain angle, and we'll call this angle alpha. So if you call the angle between the relative velocity and the tangential direction, if you call it alpha 1, okay, then you can say that the projection of W1 on the tangent to the wheel is equal to W1 cosine alpha 1. Here, if you want, W1 and V1 is the same thing, okay? So you project it, so it's W1 cosine alpha 1 or small V1 cosine alpha 1. Then at the exit, you do the same. At the exit, you decompose so this is your total velocity. It's equal to the summation of these two. So the projection of the absolute velocity is equal to the summation of projection of omega 2 and U2. And as we said, U2 is already tangent to the wheel because of rotation. So this is your wheel. It's rotating, okay? You have always that the linear velocity will be perpendicular to the radius, so it will be along the tangent to the rotating wheel, okay? While your blades can have a certain inclination. So this is the radius of your wheel, and this is your blade. The blade will orient water. So the inclination of the blade will help into orienting your water. And the relative velocity of water with respect to the wheel is imposed by the shape of the blade. And you can see here that you have always the water will be moving along the tangent to the blade. So when you talk about the velocity of water relative to the blade, it's always along the tangent to the blade. Okay, that's why if they tell you the angle between the tangent to the blade and the tangent to the wheel is alpha, then you can do your projection. You can project omega, which is the relative velocity of water with respect to the blade, on the tangent to the wheel, which will lead to rotation of the turbine blades. So now, this is the expression we get after projection. But as we said, for an impulse turbine, we have R1 equal R2. That's why U1 will cancel out with U2. And if you look at your expression, okay, we also have another characteristic for impulse turbine is that alpha 1 is equal to 0. And as we said, alpha 1 represents the angle between the tangent to the blade and the tangent to the wheel. So because it's 0, then cosine alpha will be equal to, cosine alpha 1 will be just equal to 1. So the first expression will be reduced to F equal rho Q times V1 minus V2 cosine alpha 2. Okay, so this is the expressions that we got. Now, in case we have ideal frictionless flow, what will happen is that the magnitude V1 will be equal to the magnitude V2, since we will not have losses. And in this case, for this ideal frictionless flow, we can write then that we can take V1 equal to V2, so we take it in factor, and we end up with Vf equals to rho QV times 1 minus cosine alpha 2. So this is the expression that we will get. Okay. Now, how to maximize this force? So it's clear from this equation that if I can have alpha 2 equal to 90, so if alpha 2 is equal to 90 degrees, this means that, as we mentioned, alpha represents the angle between the tangent to the blade. This is the tangent to the blade, which is along omega, which is the relative velocity of water with respect to the blade, and the tangent to the wheel. So if we can have an angle here, alpha equal to 90, so if you can have omega 2 perpendicular to the tangent to the wheel, this is the optimal case, because you will have here, this will be 0. And then you can maximize your force. Your force will be equal just to rho times Q times V. So we should try to have this angle as close as possible to 90 degrees. Okay, so now we have that, as we said, we can find the value of the corresponding power. Now, how to get your power? You know that the power is the force times the velocity. Okay, so this is how you can get the power that can be extracted. And your force, now we found the expression of the force. So the force is rho Q times V1 minus U. Okay, while for U, we have already yani this is the expression of F, and we multiply it by U. So you can see that the power is function of U, which represent, as we said, the linear velocity of rotation of the wheel, because U is equal to R times omega. Okay, so actually, now once we have the expression of the power, what is important for us, if you want, more than optimizing the force, so is to optimize the power. We need to maximize the power as much as possible. So if I want to maximize the power extracted, I just need to solve for which value of U can give me a maximum power. Okay, so all I have to do then is to say that here, this is the power is a function of small u. So let me derive this function. So I derive the power with respect to u, and I set it equal to 0. If you do the derivative, you will find out that the value of u that will maximize your power is equal to v1 over 2. So this is why we try to have u very close to v1 over 2. As we said, this analysis was based on having ideal frictionless flow, while in reality, you have always some friction. So for real flows, this ratio can vary between 0.43 and 0.48. So this is how you can maximize your power. And the efficiency of your turbine can be calculated as the output power that is extracted from the turbine over the input power. So as we mentioned, you have your dam, and from your dam you can extract water. Okay, and you can transform the total head, which was in potential energy, in rotational energy of your blades. So the maximum power extracted, which can be extracted, is the input power. The input power is just the head that you have times gamma q. Q is the flow rate, and gamma is rho times g. So this is the energy available from your dam. And the output power is the one that is delivered by your turbine. Okay. So this is how you can assess the efficiency of your turbine. Okay. So now, as we were discussing, uh, this was the analysis of impulse turbine. Now we'll do analysis of reaction turbines. So in reaction turbines, you have some different, if you want, characteristics. Okay. So first, R1 and R2 will be different. You don't have R1 equal to R2. So because R1 and R2 are different, this will change the analysis. But the overall method is the same. And first, we need to find the expression of the force F. So we find expression of F first. And after a second, we find the power by saying that the power is F, which is the tangential force, okay, times the velocity along the tangential direction. But here we should pay attention, okay, that we have to consider different values of radius at inlet and at outlet. Okay, so what we should do is we should first say at the inlet, the velocity, we have a velocity v1, and as we said, since we care for the tangential force, so when we write the total tangential force developed ft, okay, is equal to m dot, and we know that m dot is rho times q, okay, times the tangential velocity component at the inlet. The tangential velocity component at the inlet is v1 cosine beta 1, okay? And here, we know that in general, we multiply the tangential force by u, which is the linear velocity. But here, because the linear velocity is changing between the inlet and outlet, so we should multiply at the inlet by u1, okay? u1 is the linear velocity of wheel rotation at the inlet. So it's equal to r1 times omega, okay? So we replace u1 by r1 omega, okay? Minus, at the outlet, you project the velocity. So you have v2 cosine beta 2. But now you multiply by u2, which is r2 omega. So here the difference is that r1 and r2 are not equal, okay? That's why you can take in common for both terms omega outside. So you get that the power developed is rho q omega times r1 v1 cosine beta 1 minus r2 v2 cosine beta 2, okay? And now we can say that from this equation, we have first r1 different than r2, and we can maximize the extracted power. So for this turbine, our purpose is to try to maximize the power at output. This is why we say, if we look at this expression, we can have a maximum power when cosine beta 2 is equal to 0. So when we are subtracting when we subtract a term equal to 0, then we can get the maximum possible power. So this will happen for beta 2 equal to 90 degrees. Okay, so here, this is how we can design reaction turbines. So if you want, we have common formulas, but for each turbine, we have certain characteristics that should be applied in order to maximize the value of power. Now, if we consider concerning the efficiency, also the efficiency is equal to the ratio of the extracted power over the maximum power delivered, which is equal to gamma QH. So to get the efficiency of the turbine, we just have to divide the powers that we got from this expression by gamma QH, and then we get the efficiency of the turbine. Now, as we said, one of the main differences between impulse and reaction turbines is that in impulse turbine, we have the whole energy is kinetic at the inlet of the turbine, and it's transformed to rotational energy. While in reaction turbines, at the inlet of the turbine, you have energy in two forms, in form of pressure and in form of kinetic energy. And both types of energy will be transformed into rotational mechanical energy that will rotate the shaft of the turbine, and this rotation will produce electricity through um, the alternator system. Okay. Now, to define the degree of reaction of a turbine, it's given by the following relation. So as we said, whenever you have in the head, you have the pressure head, P over rho G, and you have the kinetic head, V square over 2G. Okay, so what you can do, you want to know what is the fraction of energy, if you want, due to pressure, and what is the fraction of energy due to kinetic energy. What do we mean by this? At the inlet of the turbine, let's say, you know the pressure and you know the velocity. Okay, and at the exit, you can also measure P2 and V2. And of course, because you are extracting energy from the fluid, the pressure will be reduced and the velocity also will be reduced. And because of this, you can say that part of the energy will be due to pressure reduction, and part of the energy extracted from the water will be due to kinetic energy drop. So we can define the degree of reaction of turbine as, if you want, the percentage of the energy extracted. So let us say I am extracting a certain energy E from my turbine. And I want to see what is the proportion of energy that I can get from pressure variation. So if I do delta P over rho, okay, you know, Bernoulli can be written in several forms. One of them is to write in terms of heads, or also you can write delta P over rho plus rho V square over 2, okay, plus GZ equal to constant. If you write your terms in this way, then you have the corresponding unit, okay, is energy per unit mass, because you know, if you multiply by m all of the terms, if you multiply by m, mgz is the potential energy, it's in joule, okay? So whenever you divide by m, you have all of your terms are in joule per unit mass, in joule per kilogram. So now when I divide delta P over rho by the energy extracted by kilogram from my wind turbine, I can get what is the fraction of energy that I'm getting due to pressure drop. And I can deduce then the fraction of energies that I can get from a kinetic energy drop. Okay, and for example, if you get a degree of 40%, this means that 40% of the extracted energy from the turbine is due to drop in pressure, and 60% is due to drop in kinetic energy. Okay, and in this way, you can know what is the degree of reaction of your turbine. So in this way, we introduced the different types of turbines. We'll do problems on this to see how we can do calculations and determine, let's say, for a certain turbine, what is the efficiency? Because at the end, as we said, depending on the application, depending on the value of the head and the value of the flow rate, we decide if we use impulse turbine or reaction turbine. And we need to calculate the efficiency of the turbine in order to expect what is the amount of power that can be extracted from our dam. So next time we'll do problems on this. Thank you.